Okay, so let's finish it up. Consider a class of physics students in a 3-story schoolroom with a high ceiling. The ceiling is high enough to be the ceiling of the 3rd floor. The teacher connects a long rope to the ceiling. The free end of the rope is connected to a heavy ball that almost touches the floor when the rope is vertical, creating a very large-scale pendulum where the ball travels almost completely in the horizontal direction. Wow, cool. The teacher pulls the heavy ball a small distance to the side and releases it so that it oscillates with a certain period, amplitude, and average speed. The teacher then repeats the demonstration but releases the ball from a greater displacement to think about how the period, amplitude, and average speed will change for the greater displacement. Angela says something and Carlos says something, and now we're going to A represents the amplitude distance the ball travels from equilibrium from one point to the other. T is a period. Write an equation for V average, the average speed in terms of the amplitude and the period. So the total distance traveled in one cycle is 4 times the amplitude, right? Because it's going to travel to the middle, and then travel to the other side, and then travel back to the middle, and then travel back home. And the amplitude is from the middle to one side. So we're going to go to the middle, to the other side, back to the middle, back to the original side. That's 4 times the amplitude. So the average velocity is 4 times the amplitude over the period. So the period is 4 times the amplitude over the speed. If the speed is independent of amplitude, the answer is correct, because the larger the amplitude, the longer the period. If Carlos is correct and the average velocity is much larger than the denominator, the period will be shorter. Okay. Carlos is correct. Greater amplitude will result in a greater average speed. Greater component of force tangent to the path of the ball creates a faster maximum speed. And the ball is lifted to a greater height. It has more potential energy, so it'll have more kinetic energy at the bottom of its swing. Give a correct prediction about whether the period increases, decreases, or remains the same as the amplitude increases. If the angle stays small, the pendulum will undergo simple harmonic motion, and there is no dependence on amplitude. The average speed of the ball increases with total distance traveled because both are directly proportional to amplitude. If they're proportional, then they divide out to the same period. Yeah, you shouldn't see, for small angles, the period does not matter what the amplitude is. It just depends on the length of the rope and the planet you're on. All right, we're in part H. Getting tired. They hang a spring with an unknown spring constant from the ceiling. They connect objects with different amounts of mass to the spring and measure the oscillation of each object. The data are shown in the table to the right. The square of each period is also calculated. Did not take care to ensure the object oscillated with the same amplitude in each trial. Their teaching forms of this oversight will not invalidate their experiment. Why this is the case? It's undergoing simple harmonic motion. The period is not affected by the amplitude. Graph t squared versus m. Draw best fit line. Okay, I'm sure you can draw a graph. There it is. An unknown object hung on the spring oscillates with a period of 1.4 seconds. Use your best fit line. Calculate the mass of this object. You just read this off the graph. 1.246. So 1.47 would be right here around 1.5. And so that would be here. And the mass of that would be what about? So it looks like every line is 1/3 of a kilogram, 2 1/3, 2 2/3, 2 1/6 kilograms, about 2 1/6. Oh, I forgot to square the period. I'm sorry. So I had to square the period first. That would put me up here at 2, about right underneath 2.2. And so that mass would actually be 3 1/6. About 3 kilograms. Sorry, I messed up. Using your best fit line, calculate the spring constant. The slope of the line is equal to 0.7. The equation that relates mass and period is period 2 pi m over k. If we square both sides, the equation is t squared equals 4 pi squared m over k. So a graph of a period squared versus mass will lead to a slope of 4 pi squared over k. And so we set that equal to 0.7 because the slope of the line is that. And then you could solve for k, it would be 4 pi squared over 0.7, and it got about 56. I'd love to work through that in class if you want. It's kind of complicated, but it makes sense. And some more kids made graphs. They made has a best fit line with a slightly steeper slope, and then the steeper slope would be a bigger value, but that value is in the denominator. When we get down to calculating out k, would be 4 pi squared over a bigger value, which would make it actually a smaller spring constant. Well, that's it. That's the next week, so let's stop.